Okay, well, let's now get started. And this is the example I showed you last time. So I think you still remember this problem. It's about the beer sales. And just give you a quick review of this problem. And we have 1,000 cases of beer, and it can be made in state of Washington or state of California, okay? And also we have 3 types of beer, A, B, C. Okay, so this two-way table classify this 1,000 cases into 6 categories. Okay, so each category actually here is the combination of 2 events, or the joint event. For example, this 150 cases, this means we have 150 type A and state of Washington beer, right? That's the combination, like a joint probability. So if I ask you to find the probability of intersection of 2 events, we use that number. And also, we use this table to introduce you the conditional probability. Okay, the conditional probability we did like this is the conditional probability. Here we condition on the location, Washington State beer. Okay, given that, what about the probability of type B beer? Okay, so we use the table here because Washington State is this column, so only this column is relevant. So it's going to be 450 to be the denominator, because every case here is a possibility, right? So out of 450 cases, how many cases are type B is 250. So 250 over 450. So we got that probability. Similarly, you can also compute the conditional probability on type. Okay, like given type B, what about the probability that we have California beer? It's going to be 250 over 500. So either you condition on column or you condition on row, you can find conditional probability, right? It's pretty clear. And how about joint probability? The joint probability is different because the joint probability, we don't have any information given. We don't have like a vertical line, like given something. So here, for example, if I ask you the probability of B and WA, remember that? This probability is joint probability. But here we don't have any condition. So we don't have a vertical line and then condition like event, location, or type. We don't have those conditioning event. So we have to use this 1,000 as denominator, because if you don't have any condition, then every case is a possibility. So you have to use the total number here, 1,000, as the denominator. And now how many cases satisfy both conditions, like when both events occur? Okay, B is here, WA is here, so the intersection is here. So that's why we call it intersection probability. So 250 over that will give you the joint probability. Okay, so with the joint probability and unconditional probability here, okay, we can get a formula here. The formula is right here. Okay, that's a quick review here. So the formula is if you divide the joint probability by unconditional probability, this is called unconditional or marginal probability. So then you get the conditional probability. Okay, so this formula is fundamental. You need to memorize that. And it's not difficult to memorize this formula because the conditional probability here, okay, is equal to a joint probability divided by unconditional probability. Or you can call that marginal, right? Marginal probability. And the numerator is always the joint, so B and WA or WA and B, either way, okay, so it's a joint probability. But the denominator here, it depends on here. if you condition on WA, then you have to divide the joint probability by P of WA. Never divide this by P of B, then you are wrong. Okay? You have to use the conditioning event. That's important. Okay, I think that's a good review of what we did last time. It's good enough now. I think everybody knows. Any questions or comments you want to make here? Well, let me open the any questions about conditional probability. No problem, right? Okay. Let me open our PowerPoint notes here. Okay. All right. Now, we continue that chapters 4 and 5. Chapters 4 and 5. Right here. Okay. I think we are here now. Right? This table. Right? We did that. And also we got this formula. So P of B given A equals P of A and B divided by P of A. And we also did that problem. So I don't want to repeat that. And the good thing about this formula is we can get a multiplication rule here for a more general case. So now how about if A and B are dependent? Okay, they are not independent. Then we have to use this formula. P of A and B equals P of B times P of A given B. Okay, you know why we get this formula? Because if you use the conditional probability here, you have this. Is that right? You have that. Okay, if you have this, then you can multiply both sides by P of B to get this. That's very simple algebra. So you multiply both sides by P of B, you got P of B times P of A given B equals P of A and B. So you see that? So P of A and B equals P of B times P of A given B. That's the multiplication rule, which simply says that if you want to find the joint probability, you just use a marginal probability times a conditional probability. But here you have two options. You can either condition on B or you can condition on A. So this is only one option. So can you give me another formula for P of A and B? Anyone? P of A, good. Times?
P of A, or, yeah.
P of B given A, you're right. Yeah. It's good, it's right. So we have two options. So either you condition on B or you condition on A. But you have to be consistent. So if you use P of B, you have to condition on B. If you want to use P of A, you have to condition on A. A very likely mistake is that people write P of B here, but then they use P of B given A here. That's totally wrong. You have to be consistent. Okay? So now we have a general formula for joint probability. This formula always works. This formula always works. Why? Because even they are independent, this formula is still true. Why? Because we know if A and B are independent, How about that term? If they're independent, how about P of A given B? Tell me. If they're independent, how about P of A given B? Do you think that B matters? No. So that means P of A given B equals what? Just P of A. Do you agree? Because it doesn't affect the probability of A. So if they are independent, this conditional probability becomes unconditional probability P of A. So this formula is reduced to P of B times P of A. Do you follow me? You okay? Good. How about that? Same thing. A and B are independent. How about that term? Given A, probability B is same as P of B. So this becomes P of A times P of B. So that's why this formula is so general. Okay, even they are independent, it's okay. This formula still works. Okay, that's okay. Let me. I think we also did another problem last time. I think that's where we start. Okay, let me go back to here. Sorry, I have to switch back and forth here. And this problem is quite easy to do now. Okay, 25% of students studied at least 3 hours per day, and we also know 40% of students who studied at least 3 hours per day have a GPA of 3.0 or better. What's the probability that a randomly chosen student studies at least 3 hours per day and has GPA of 3.0 or better? Did we do that problem? I forgot. No? Okay. Good. Let's do this problem now. I think everybody can do it. It's not that difficult, but I want to go through that example here. Okay. We have two events of interest here. First event, okay, is study time. I put study time. I think that's easier to write. How about that? I think that's pretty clear. That's event A. Okay, so that's event A. How about the next event? Let me read the question. 25% of students study at least 3 hours per day. 40% of students who study at least 3 hours per day have a GPA of 3.0 or better. So that means we have a GPA event. You can use any letter, okay? You can use B or C or any letter, but I prefer to use a G to represent the GPA. I think that's more meaningful. I use the letter G. So here, I put the GPA is 3.0 or better. So I have two events. Is that clear? Okay. Now, after these two events are defined, we can write down the numbers given from the problem in terms of those events. Okay, so here we have 25%. 25% is 25% of students study at least 3 hours per day. So apparently P of A is 25% because the proportion is also the probability. Any questions? It's clear, right? Okay. How about the next number? 40% of students who studied at least 3 hours per day have a GPA of 3.0 or better. Here, this 40% only applies to a special group, not for everyone. Which group? The group of students who have studied at least 3 hours per day. So that is a condition. That's a condition. So here a condition on what? Condition on A. Given A, then the chance that this guy has GPA of 3.0 or better is higher. So it's how high here? It's 40%. Is that right? So that's two conditions given. Two numbers given. I write given. Okay, what do we want? Let me read the question. What is the probability that a randomly chosen student studies at least 3 hours per day and has a GPA of 3.0 or better? So we want both and. So the event will be that. First, they study at least 3 hours per day. Secondly, the GPA is 3.0 or better. Both. So we are computing the joint probability. Can you write down P of A times P of G here by using our simple multiplication formula, P of A times P of G? Can we do that? Yes or no?
Yeah.
Can I write that? P of A times P of G.
No.
No.
You're right. Say no. Why not?
Not independent.
Perfect. That's a good answer. They're not independent. I think that is true. Because if the guy studies a lot harder than the others, like more than 3 hours per day, then the chances are better. They have a better chance of getting GPA of 3.0 or better. So they're not independent. You're right. So here you cannot use P of A times P of G. You have to use our general formula. The general formula is P of A, okay, times P of G given A. Is that right? So it's going to be a marginal probability times a conditional probability. But here you have two options. You can either use P of G times P of A given G. You can do that. The formula is right. But you get nothing because you're not given the numbers. Or you can use P of A times P of G given A. You have to be consistent. If you use P of A, you have to condition on A. But this option is better. Why? Because look, numbers are given. Okay, so now you just plug in the number here. You get the answer, 10%. Okay, so that's quite straightforward example. Okay, it's not difficult at all. You just use the formula, and you get the answer. So that's an example of using the formula. Okay, using the general, we call it generalized multiplication formula. Any questions? If you have any questions, please ask. Okay, now, if I show you this slide, okay, I think it's pretty clear. You should be able to understand every point. The first point is about our multiplication rule, okay? P of A and B equals P of B times P of A given B. You can also write P of A times P of B given A. It's also good, okay? And because of conditional probability definition, okay, we know how to define conditional probability. We can find 3 equivalent conditions for independence. The first one is familiar to everyone. We know this, right? Our first multiplication formula, when A and B are independent, P of A and B equals P of B times P of A. So if this is true, the 2 events are independent. So in any problem, if you have P of A and B, you also have P of A and P of B, then you can check whether or not the 2 events are independent by using this condition. If they are equal, they are independent. If they are not equal, they are dependent. Okay, so that's our basic condition. But because we have conditional probability definition now, we can also use this as the independent condition, because this is actually the mathematical expression of my independence definition. Because P of A given B equals P of A, what does that mean? That means given the event B has occurred, the probability of A is not changed. It's same as P of A. Can you see that? So that means they are independent. Do you remember the example about writing an exam? Like, for example, next week you write midterm 1, okay? And event BA is the chance that you get A in that exam. And event B is that there's a car accident in Seattle, downtown Seattle. Okay? Both are possible, right? We know P of A, maybe getting A is you're a good student, you have studied a lot. So the chance is 90%. You get A. How about B? B is that there will be 10% chance in downtown Seattle there will be a car accident on that day. So now let me say P of A, you know, is 90%. How about now I tell you, given that Seattle has car accident, what's the chance that you get A? I think that is still 90%. Do you agree? Your performance is not affected by the car accident. So both are equal. See that? Everybody follows me now? Numerical example. And similarly, you understand that. We just change the letter. So now, when I ask you to check whether or not the two events are independent, you only need to check one of the three conditions. You don't have to check all of them. Because if one condition is true, the other two must be true. You don't have to check, okay? So now you know how to answer my question in the test or assignment if I ask you whether or not the two events are independent. You can actually use my beer sales example now to check whether or not the beer type and the location are independent. You can use one of them to check, because you can figure out those probabilities from the two-way table. I don't show you example now. You can do it. I trust you. You can do that now. Any questions? Here's an exercise of using the formulas we have learned and the concepts of independence. Here, suppose that 50% of husbands watch a certain TV program independently of their husbands. 30% of wives watch the same program. And if husband watches the program, what is the probability that the wife watches it? I think that's easy now. Everybody can do it. I mean, let's quickly do that. I'm not going to spend too much time now. I'm going to go over this quickly. Okay, first I will define the events of interest. We have two events of interest here. We have H and W. I think that's two letters I like to use. H means husbands. So H is husband watching the TV program, and W is this, right? So wife. So that's my example here. And I'm not switching back to the problem, and now I'm reading this for you. 50% of husband watches this program, so P of H will be 50%. Is that right? That's pretty clear. Yeah. And how about 30% here? This is for wife. A very important condition is that H and W, this is important. H and W are independent. Okay, now let's do A. A is that if the husband watches the program, if the husband watches, I can write that, given H. What is the probability that the wife watches it? Do you agree? Okay. You bet. Well, that's why I said it's easy. Okay, this will be 30%. You're right. Why? Because you know that this is equal to this. Why? Let me tell you. In general, they are not equal. In general, they are not equal. I think in real situation, they are not equal. Husband and wife may, their decisions may be not independent. Okay, but here we are given the condition, so we can write equal here. Then the answer is 30%. You're right. How about B? B, let me read that. What is the probability that at least one of the husband or wife watches the program? The key word is at least. At least means what? Means either wife or husband or both, which means the union of the two events. So here we are computing this. Husband, union, wife. Okay, so that's the event we want to find this probability. Okay, so here we certainly have to use our union formula. I think everybody remembers that. You remember that? P of H plus P of W minus P of H and W. That's our union formula. Okay, that's our union formula. P of H and P of W are given. because we have 50% and 30%. So these two numbers are easy. How about the third term? We're not given this number directly, but it's not a problem. We can get that. How to get that? 0? I heard that 0. 0 means that it's never possible that both watch the same program. I don't think that is true. Yes! Got the answer here. Multiplication. Why can you multiply them? Yes. So here, you can simply write P of H times P of W because of this. If we don't have this condition, you cannot multiply these two probabilities. Okay, so here you can because of independence, so it's 0.5 times 0.3. Everybody follows? So we got the answer now. This is 80 minus 15, 65%. 65% chance. So that's the answer to the second question. The probability that at least one of husband or wife watches the program is 65%. Questions? Is it clear? Okay, that's very good. So that's pretty good. So now we know how to solve probability problems involved conditional probabilities, or marginal probability, and joint probability. But sometimes the problem is getting more complicated. So it's better to use a tree diagram to solve the problem, because using a tree diagram makes your problem more clear. Okay, in particular, if you have to deal with a lot of conditional probabilities. The Venn diagram is very good for showing the intersection or union, but it's not convenient for showing the conditional probabilities. That's why I want to show you another useful tool, okay, a graph or diagram to solve the problems. So the tree diagram is a probability tree. That means we have to give the probability information on the tree. Okay, I use a very simple example to show you how to make a tree. Okay, then you can apply this technique to more sophisticated, more complex problems. Okay, let's now look at the probability tree problem. Okay, a ski resort makes a profit 3/4 of the weekends when the weather is favorable, but only 1/8 of the weekends when the weather is bad. So apparently, we have two conditional probabilities given, 3/4 and 1/8. Both are conditional probabilities, and they condition on weather, okay, bad weather or good weather. And the probability is 2/3 that a weekend has favorable weather. Then we want you to find the probability that a company makes a profit on a weekend. It's not a very big problem. It's a small example here, but it shows you how to make a tree diagram. So that's why I want to use this example here. Okay, just like any probability problems, we first define the events of our interest. So here we have two types of events. The first type of event should be weather. Okay, so I'm going to put a F. F here means how about that? F is favorable weather. Okay, if F is favorable weather, how about bad weather? If by reading the question you see that we only have two categories, either good or bad. Okay, we don't have like a semi-good. just two. So then if you just have two outcomes for this event, you can use event F and its complement. Because then you can save a letter. You just use the same letter F, but you use F complement. That means bad weather. Do you agree? Good. That's type 1 event. Type 2 event is the business event. The business the business outcome, we either make a profit, I use M, or we don't make a profit. Again, two possibilities. So you can still use complement. That means not making a profit. So we only need 2 letters. We only need 2 letters.
How about make it even, just variable profit and a negative profit?
Well, you could do that. Like you can use 3 possibilities. But in the problem here, we only care about what's the probability that the company makes a profit. So you make the profitable example as one category. The remaining will be, the complement. Okay, not making profit. Certainly, if you want to know more details, if you have more data, you can certainly have 3 possibilities, like break even, negative profit, positive profit. You can do that. Okay, that's a good comment. Any other questions or comments? So far, so good, right? Good. After defining those events, we can write down the numbers given in the problem. We are given several numbers here. The first number is 3/4. I told you that is conditional probability. The 3/4 chance, 3/4 of weekends, we make a profit if the weather is good. So that means this. Do you agree? Given weather is good, given F, the probability of M is equal to 3/4. How about given the weather is bad, given F complement, the chance that you make profit 1/8, right? Much smaller, which makes sense. So this business, skiing. So that's okay. How about 2/3? 2/3 is the chance that we have good weather. So P of F is 2/3. Those numbers are given. Now we are ready to make a tree. I'm going to make a tree here. I think that space is good enough because of small problem. Problem is not that large. The tree diagram starts with one single node. Okay? First, you graph the weather event. There are only 2 possible outcomes. So you're going to have 2 branches. One branch represents good weather. The other branch represents bad weather. That's easy. How about second stage now? Another node. Here, we're considering the business event. Either we make a profit or we don't make a profit. Is that right? So here I can put making a profit or not making a profit. Here we do the same thing. Making a profit, not making a profit. Everybody follows? It's not hard, right? So that is like a tree. Is this right? Is this tree right so far? Not 100%. Not 100% correct. Why? Because here, when you graph this branch here, it represents conditional event. You condition on what? Good weather. So precisely speaking, you should put this. That means given the weather is good, we make a profit. That's condition. Similarly, here you should put the condition, right? Everybody follows? Now I'm going to put this is F complement, this is F complement. Now it looks better. Okay, so we should use conditional events. This is like a tree diagram, but we cannot call it a probability tree because we haven't put probability information on the tree. So next, we're going to figure out the probabilities. Last, to complete the tree here, also you need to indicate the terminal outcomes. So we have 4 terminal outcomes. Each terminal outcome represents the combination of the 2 events, or the joint event, the intersection, right? Here, this node means what? This means we have good weather and we make profit. And here is we have good weather and we do not make profit. And here is we have bad weather, we make a profit. And here we have bad weather, we do not make profit. So we should have 4 basic outcomes, or terminal outcomes. Why we call them terminal or basic outcome? Because they make up the sample space. Some of them must be 100%, or at least one of them occurs for sure. Is that right? Okay. So the tree is completed. Now the last step is to put the probability information on the tree. Okay. That's not too hard because we are given those numbers. So let's first put probability of f here, which is given, is 2/3, right? It's 2/3. That number is given. How about the probability of bad weather? You can tell me right away. 1/3. Very good. Well, we know that is event f and its complement. Some of them must be 100%. Actually, that is the property of the probability tree. For probability tree, every node, the sum of the probabilities on the branches from the same node must be 1. That's the property. Okay? If you created a tree diagram, you have to check that to make sure that the probabilities, sum of the probabilities on the branches from the same node must be 100%. Okay? That's the requirement. So because of that, you can certainly complete the tree quickly now. Because this is given, right? This is 3/4. Then how about here? 1/4. You got it. How about here? This is given. This is 1/8, right? That's 1/8. If this is 1/8, how about here? 7/8. You're right. I think everybody follows this. It's not that hard. Finally, we need to figure out the terminal outcome probability. Those probabilities. Okay? How to do that? Well, you can certainly use the formula we learned. Like here, you can say, well, I use the marginal probability of P of f, then we times P of m given f. Remember that? That's the multiplication formula. You can do that. This will be P of f times P of m given f. I'm using the formula. But P of f is here. P of m given f is here. So it's going to be 2/3 times 3/4. Is that right? So it's just this times that. This is true. But from this example here, you find that we can actually follow this route from starting node to the ending node. Then you multiply the probabilities on the route. So it's going to be this times this. You get the probability of terminal outcome. And that rule is true for the probability tree. And that rule actually is more convenient than using formula. When your tree is getting bigger, you have multiple stages. So you don't have to use a formula. You just follow the route from starting node to the ending node. You multiply the probabilities on the route. That's a much better way than using formula. And actually, that's one of the advantages of using probability tree diagram. Everybody follows? Okay, good. So you know how to do that. Certainly you can figure out the probability of this. This will be what? Will be 2/3 times 1/4. So now I'm not writing the formula. I just give you the answer now. So this actually equals 6/12, right? Or maybe you feel that, why don't we just simplify that to 1/2? You can do that, but I would rather keep the complex form because I'm going to use this number later. Okay, let's just keep 6/12. So how about this root? This root from here to here is going to be 2/3 times 1/4. 2/3 times 1/4. So this gives you 2/12, right? How about that root? I think I can do this quickly. 1/3 times 1/8. So it's 1/24. How about this? This will be 7/24. You know what I'm doing now. Everybody's clear? Any questions? Okay, good. This is the complete probability tree. Okay, from this tree, you can get any kind of probability. Like in this problem, what do we want? Let me read the question. The question is, what is the probability that the company makes a profit on a weekend? So we actually want this probability. Do you agree? We want you to compute that, P of M, probability of making a profit. I don't care about whether. I just want to know what is the chance that we make money. Now, you can get that from this tree. Why? Because look, you know this one of the 4 outcomes will occur for sure. But which outcome represents making a profit? Only 2 of them. Number 1, this one means you are making a profit. How about this one? No. How about this one?
Yes.
How about this one? No. So only 2. Right? Either good weather and making profit, or bad weather and making profit. So these 2 events make up the event of M, and they are destroyed. One and only one occurs. Therefore, you can add the 2 probabilities. Remember that rule? Addition, we call it addition rule. Like if A and B are destroyed, then P of A plus P of B equals P of A or B. So here, you can write P of F and M plus P of F complement and M, which is this probability plus this probability. Everybody follows? And the answer will be 6/12 plus 1/24. So the answer is 13/24. Is that clear? Good. That's the probability that the company makes a profit on a weekend. Good. Well, I'm pretty sure you are quite clear about the probability tree now. But I want to actually expand this result here a little bit. I want to talk more about this formula, because this formula actually is kind of a decomposition formula, because your event of M has been decomposed into 2 sub-events. Okay? And decomposition helps in solving probability problems. But this decomposition can be represented by a diagram.